Hi, everybody. We'll get started here in a couple minutes. Thanks for your patience. All right, everybody. Thanks for joining in this afternoon. I'll go ahead and share my screen. So would someone kindly unmute and let me know if you're seeing the screen share as the course homepage is up?
Yes, ma'am.
Thank you very much. So I will let you guys know up front, today's session is not going to be, well, it's not going to be as long as we typically meet. We normally have been running about an hour to an hour and a half, depending on the number of questions. But today, I'm gonna try to do things in a kind of an expedited fashion and rely on you guys' professionalism in that if you have questions, feel free to reach out to me. I try to make myself as available as possible. So beyond today's meeting and the information that I share with you, I hope that you will reach out to me with any questions that you might have. And, you know, I appreciate those of you who regularly join in and ask questions, whether it's here or in an office hours visit or by email. Again, don't hesitate to reach out to me. So just as a reminder, this session is being recorded, and as with all sessions, I will share the recording in the announcements. It'll take me a day or so to get it posted because I do like to get our videos captioned, and that sometimes takes a little bit of time, sometimes up to 24 hours or so. Okay. So with that being said, I'm going to get into the weekly overviews. And you can see we're moving along here quite nicely. In fact, we don't have many actual sessions that we're going to be meeting for today and then next week, and then the following weeks we'll talk about. Okay, so let me jump into this overview, the thermodynamics overview. So you see here listed the objectives for the week. So when you finish with this material, You should have a better understanding of heat and temperature, and the scales that we use for temperature. You should know how to convert from one temperature scale to another, although that's not something that I focus on too heavily, because at this point, you can use the unit converter or a conversion chart or any tool that you like to help you make those conversions. So it's not something that we're going to directly practice, but it's something that you can use any resource you want to help you. We'll look at various heat transfer applications, like those that involve a temperature difference and those that involve a phase change. And we'll talk about the difference between the two. And we'll talk briefly about the methods for heat transfer. In other words, how does heat get transferred utilizing any of the methods that we'll talk about. And as in the process of talking about the different phase change relationships, we'll look at the formulas involved for specific heat and latent heat. And then we'll focus on thermodynamics a bit, primarily the first law of thermodynamics. That's where we spend the bulk of our time regarding thermodynamics. Okay, so any questions about the objectives for this overview? Okay, to help you along with that material, I've made available to you chapter 19 in our textbook. There are some videos from on thermodynamics from Khan Academy. There's also a very nice website that NASA provides that deals with thermodynamics, and we may even take a look at that when I talk about the first law of thermodynamics. And then, of course, you see all of my notes here, the supplemental notes. So I will tell you right up front that there may be some portions in these notes that we won't focus on as heavily, but they're available to you if you want to utilize them at any point, okay? So the first one I'm going to go to and is the temperature notes, okay? And the reason being, before we can talk about heat transfer of any kind, we need to understand temperature. And then we'll do the heat notes and finally end with the thermodynamics notes, okay? So let me see if I can, there we go, okay. All right. So these objectives that relate to temperature are the ones that are found in the weekly overview objectives. I pull them directly from there. And so you can see here that while these notes deal with kinetic theory and the gas laws, I don't focus on them here in this course because if you take a chemistry course, you will definitely be exposed to those in greater detail. So I'll save that for the chemistry course that you have to take. All right. And so my focus in this packet will be on temperature. So, I mean, in some respects, temperature is not a foreign concept to you because it, in simple terms, it deals with hot and cold, right? But we know, because we're in a physical science course, that we can't just talk about things like feels hot or cold, because each person will perceive things differently. What I perceive as cold, you might perceive as warm. Or, if I think something is hot, you might perceive it as cold. So that's a personal perception, that hot or cold. And so we need to go to a more quantitative description. And that is why we turn to this notion of measuring temperature, which brings about the need for a thermometer, which is the instrument or tool that we utilize to measure temperature, okay? And so, you know, the thermometer involves reading a scale, and so we need to know what scales we utilize. Now, in this country, no doubt you have exposure and experience with the Fahrenheit temperature scale, because, for example, if you turn on the news and they're talking about the weather, inevitably they will talk about temperature, and they measure that temperature on the Fahrenheit scale in the US. That's our common unit. But when we're dealing with scientific measurements, in particular in physical science, we turn to the Celsius scale, number one, or the Kelvin scale. And now the Celsius scale is based on the freezing point and boiling point of water, which is 0 degrees C for the freezing point and 100 degrees C for the boiling point. And while this scale works for most applications, the fact that it depends on the freezing point and boiling point of water introduces some variability in our, in measurement. Meaning, as the atmospheric pressure changes, the boiling point and freezing point of water also changes. And so that introduces some inconsistency. So if you're measuring the temperature of boiling water in Celsius and you're in the mountains of Colorado, you might get, a different value than what I will get as the boiling point in New Orleans, Louisiana, because they are, at different elevations and therefore at different, they have different atmospheric pressure. But for most things, the Celsius scale is just fine. If you're working in a in a laboratory setting, like a chemistry lab class or something like that, and you have to use a thermometer, or even if you're taking the face-to-face lab class with one of the other instructors and you have to measure temperature, most likely you will use a Celsius thermometer. And for most purposes, it works just fine. You just, you have to be aware of the potential inconsistency. And so to combat that, or to overcome that inconsistency that arises due to atmospheric pressure, we turn to the Kelvin scale, okay? And notice they give you some very specific scientific literacy information here. When you talk about the Kelvin scale, you do not use a degree sign. So notice we said degrees Celsius, that little circular symbol looks like is for degrees. But when you're doing Kelvin, you don't do that, okay? And the other important factor that helps us to overcome that, issue with atmospheric pressure that the Celsius scale has to, deal with. The Kelvin scale is what we call an absolute temperature scale. So it's not based on the boiling point or freezing point of water. It's actually based on something called a triple point, but we don't have to really get into too much detail here about that. The main idea is that on the Kelvin scale, 0 Kelvin is the lowest temperature possible, and that's called absolute zero. And that's important because absolute zero is the temperature at which all molecular motion ceases, that meaning the system has zero energy. And while there are many scientific processes that are very close to absolute zero, it really is a theoretical kind of temperature because we're getting close, but we have not hit that. And theoretically, because it's the temperature at which you have no molecular motion, that's not something we can necessarily obtain in a laboratory setting, right? Theoretically, we can talk about it, and we can even talk about ideal gases and those types of constructs, but they their models to help us in a simplistic way so that when we deal with actual gases or actual temperatures, we have something to shoot for, okay? So on this Kelvin scale, or the, the scale where we take absolute zero as 0 Kelvin, there's a connection between the boiling point and freezing point in Kelvin and in degrees Celsius. So the way you get that temperature, you can easily see, is to add 273.15. So 273.15 Kelvin is the freezing point, and 373.15 Kelvin is the boiling point. Now remember, the nice thing about the Kelvin scale is that while we have a relationship between those temperatures, I mean, you can convert between those temperatures, the Kelvin scale is not based on the boiling point and freezing point of water, okay? And they make something, they tell you something very important here as well. It says, note that the magnitude of the units in the Kelvin scale is the same as in the Celsius scale. What are they talking about there? They're talking about the temperature difference between the boiling point and freezing point. On the Celsius scale, the difference is 100 degrees Celsius. On the Kelvin scale, the difference is 100 Kelvin. So the temperature difference is the same on the Kelvin scale and the Celsius scale. Notice I didn't say the temperature is the same. I said the temperature difference is the same, right? Because we're just talking about magnitude. How many steps would you have to take to go from freezing to boiling on either scale? 100 steps, okay? 100 units. So they give a nice visual here that shows you the comparison between the two scales. And you can see the comparison there, okay? So they're showing that the temperature in that little, you notice they have 5 degrees Celsius, 5 Kelvin on the far right. What they're reminding you is that the temperature difference is the same. The magnitude of the temperature difference is the same on either scale, okay? And then, just a nice visual to kind of get you thinking about in nature, some actual processes that happen in nature or some actual scenarios in nature. What kind of temperatures are we talking about? So you notice it says what? The lowest temperature ever observed outside a laboratory is 1 Kelvin within the Boomerang Nebula, which is about 5,000 light years from Earth. Light years is actually a distance and not a time. So they're telling you how far away the Boomerang Nebula is. And they've observed through some real fancy laboratory techniques, that lowest temperature, 1 Kelvin. And notice they said that, one of the hottest temperatures, if you know this, is the interior of a neutron star, which is 1 billion Kelvin. That's kind of extreme, if you will, in terms of the lowest and the highest, right? But look at, the surface of our sun is about 3,000 Kelvin. So compared to some other temperatures, the surface of the sun is pretty cool. We think of the sun as being, our sun as being extremely hot, but its surface temperature compared to some of these listed on the diagram here is really low. There are some different types of thermometers. We are not going to get into the different types of thermometers, meaning what are they made of. Just need to understand that whatever material is being used, it responds to changes in temperature. I mean, you wouldn't want to be using a material that doesn't respond to temperature changes if you are trying to, use that as a thermometer. So that's the only important thing there. We don't really need to go deeper into that. I'm not testing you on whether you know what a thermometer is made of. I'm sure most of you have seen thermometers that have mercury, mercury-based thermometers. And then you see there are some other metals that they design thermometers with. Okay, so now it says here, this absolute zero. Recall I just mentioned that the Kelvin scale has as its lowest temperature absolute zero, and that the concept of that absolute zero arrives from the behavior of gases. I mentioned the fact that this idea of ideal gases, right? And so in studying the behavior of gases, this concept of absolute zero arises. Okay, and so in studying the behavior of gases, scientists noticed that for any gas, as you look at the relationship between pressure and temperature, there's a relationship such that the behavior of all gases when plotted, think of a graph where you're plotting pressure and temperature, that always extrapolates back to the same temperature of 273.15 degrees Celsius, which corresponds to what? 0 Kelvin, right? And this kind of, leads to the theoretical idea that that's the lowest temperature possible. And so it's designated as absolute zero. And as I mentioned, that is the temperature at which all molecular motion has ceased. So think about it. If you don't have anything moving, you don't have any kinetic energy, right? So, so that's, and the reason why the Kelvin scale starts at absolute zero or 0 Kelvin is because of its relationship to the behavior of an ideal gas. Just like absolute zero is a kind of a concept, this idea of an ideal gas is a concept. So we model real gases based on the theoretical constructs of absolute zero and an ideal gas. We won't get to, I'll just briefly mention this zeroth law of thermodynamics. And it's funny because typically you think first law, second law, third law, but after scientists found those other laws, they realized that there was something even more fundamental that is based on temperature, okay? And so they call that the zeroth law of thermodynamics. So go back and, after you found the first and second law, go back and set up the zeroth law. So they weren't exactly figured out in order. And basically what it says is, and if you're thinking about this, you might have had opportunity to experience what they're talking about here. So imagine if you have items that are at different temperatures and you bring them in contact with each other. So if these objects are in contact, you're going to get some heat transfer. And then that will keep taking place. The heat will be exchanged between those items until they reach thermal equilibrium. And at that particular state, once they reach thermal equilibrium, or once both systems are at the same temperature, you won't get any heat flow. Okay, so these objects that are in thermal equilibrium have the same temperature, and that is the crux of the zeroth law of thermodynamics. Things at the same temperature, things that are in thermal equilibrium, will not create any heat transfer. right? Or will not have any heat being transferred between them. So that they stated formally in terms of two systems, A and B. Okay. And this other system, C. Typically, they think of this: if you have if you have water in two containers and you are able to bring those two containers in contact with each other and manipulate them in a way that they could, the water in those two containers could mix. Eventually, they'll settle down and be at the same. Everything will be at one temperature. And if you put a thermometer in that, you think of that as system C. And so you won't be getting any heat transfer in the water, and you won't be getting any temperature change in a thermometer, okay? Because everything will be in thermal equilibrium. But a simple way, objects in thermal equilibrium have the same temperature. And that's why I mentioned the zeroth law right now, because it does rely on your understanding of temperature. We don't get into linear expansion, thermal expansion. We don't really beat up the ideal gas law. It's just that you need to understand that ideal gas is not a real gas, but it does allow us to simplify things enough so that we can understand the behavior of actual gases. We don't deal with Avogadro's number. That's chemistry. We don't focus on kinetic theory here. I try to keep the math at a simple enough level, and we're not going to go there to deal with kinetic theory. I will introduce the phases of matter concept here, because when I talk about heat transfer, especially as it relates to a phase change, you'll need to know something about the phases of matter. And so the three common phases of matter are solid, liquid, gas that we're concerned with. There are actually others, like plasma as an example, but we don't get into that here. So solid, liquid, gas. And then what we'll look at when we talk about heat transfer is what has to happen for a material or matter to change from one phase to the other. What you do need to understand about these phases of matter is that out of the three phases, gases are typically the most energetic of the phases. So material, if we compare water in solid, liquid, and gas form, the gas form would have molecules that are more energetic, hence at a higher temperature. Okay? For most substances, things behave that way. And you can see here this idea of the triple point. The triple point, and you see they're talking about the triple point. That is where you have solid, liquid, and vapor phases, solid, liquid, gas, existing in all three phases simultaneously for water. Dalton's law, we don't need to get into that either. Those things that deal with gases and the laws, you'll definitely come across that in chemistry. Okay. I'm not necessarily interested in humidity and dew point either at this particular juncture. But you know, of course, I will say this: if you live in Louisiana, I don't have to tell you too much about humidity. You deal with it all the time. Okay. So temperature. The basic idea is that temperature is a quantitative way to specify hotness or coldness of a substance. There are three temperature scales. We focus primarily on the Celsius and Kelvin scales. And beyond that, you know, the idea of absolute zero, and just a brief understanding of the zeroth law of thermodynamics. Okay. Any questions on these notes that I've just covered dealing with temperature? All right.
So the stuff that you briefly went over is something that we really don't have to focus on.
The stuff that I said skip,
Okay.
stuff you don't have to focus on. The things that I spent some time explaining, those things you do need to understand.
Okay.
That makes sense to you?
It does.
Okay, just want to make sure that I'm not confusing anybody regarding what's what's important and what's not. And for some reason, things are wanting to take their own sweet time to load up here. Let me see if I can try it again. Okay. They're there, just didn't want to open. Let's see if I can do this another way. I might have to stop the share momentarily to open this for you, because I don't know if you'll be able to see it right away. So let me just share my screen again. And now you should be seeing, this is what the packet looks like. Canvas was being temperamental. So if you ever run into that problem where you're trying to view the notes, the ones that have the little arrows beside them, they're downloadable. So you could try that if you ever have it happen where it looks like it's kind of frozen. Just download it. Okay. So these objectives that relate to heat transfer are the ones that you'll find in the weekly overview under the objectives tab. So these things will be focused on in this packet. All right. So what is heat? You know, I've used that word a couple of times already, but I hadn't really given you a formal definition of heat, right? Well, in some respects, just like, you know, a formal definition of temperature is helpful in physics and physical science, but it doesn't mean you don't have your own kind of understanding of heat, right? But we just need to be careful that we utilize it in the formal sense of the word when we're dealing, you know, in this environment, right? In this course. So notice something that's very important in the definition of heat. Notice that word is spontaneous. That's a very important word. That word spontaneous means you don't have to force anything. It happens all on its own. In other words, it's a natural process. It's the way nature behaves. So heat is this spontaneous transfer of energy because things are at different temperature, right? So if you bring a hot object, for example, if you take a hot piece of iron and you dunk it in water, you're going to have some heat being transferred from the hot iron to the water. And that's going to happen all on its own. You don't have to provoke it in any way. Now, eventually, both of those objects will settle down and they will have the same temperature, and then they will be in what? Thermal equilibrium. But as long as there's a temperature difference, you're going to have this energy transfer. So something I want you to be thinking about is this idea that heat and energy are interchangeable. You can transfer energy, and if you're transferring energy, there may be some heat transfer that's going on, right? Heat exchange. But I also want you to think back in a way that you go back to when we talked about energy. And that was one of the things that I highlighted then, was that work and energy are interchangeable. So now we have work, heat, and energy that are interchangeable and interrelated. And the relationship between work, heat, and energy forms the basis for the first law of thermodynamics that we'll talk about here momentarily, okay? And so now, you know, in everyday conversation, we kind of mix the words heat and temperature up to mean the same thing. But in physics, it's very important to distinguish between temperature and heat. So a temperature of an object is a measure of the average kinetic energy of its atoms and molecules. So when you're taking the temperature of a substance or an object, what you're figuring out is what you're actually measuring is how energetic are the atoms and molecules that make up this object or substance. Heat, on the other hand, tells you about how much thermal energy that object possesses. And that thermal energy is dependent on a few things that we'll see here in just a few moments. But just to kind of, you know, at an introductory level, we need to understand the difference because, for example, it gives a nice example here. If I had a glass full of water and a swimming pool full of water, they can both be at the same temperature. You can stick your thermometer in either one of them, a glass full of water or a swimming pool full of water, and they could have the same temperature. But because we're looking at heat from the perspective of the molecules and atoms, the swimming pool is going to have a whole lot more thermal energy or heat because you have much more of it. Okay? And so the average kinetic energy of the water in the swimming pool and the water in the glass can be the same. But the pool, because you have so much more water, so many more molecules, is going to have a lot more heat or thermal energy. Okay. And there is a relationship, as I mentioned, between heat and work. We just saw the definition of heat as it pertains to energy, but now let's explore the relationship between heat and work. And so they can be converted. They're exchangeable. You can exchange mechanical work. You can, you know, convert it to heat, and then you can utilize heat to do mechanical work. All right. And so they give the example here of stirring a liquid. Well, think about it. If you have a paddle that you're stirring, there's some motion involved with that. That motion is mechanical. That's a mechanical type action, right? But as you stir it, that mechanical energy gets, you know, gets converted to heat, which ultimately causes the temperature of the substance to go up. Okay. And then, so, you know, a lot of times if you go to like a kid's museum, they might have like where you ride a bike. And as you ride a bike, as you pedal the bike, it turns a big set of paddles, rotating paddles in this big container of liquid, typically water. And there's a thermometer attached to it, many times a digital type thermometer. And as you paddle, you can actually see the temperature of the water increasing. So you've taken mechanical work and converted it to heat energy, which ultimately raises the temperature. Okay. Now, this relationship, you know, is pretty important that humans figure that out. Okay. This physicist James Prescott Joule was the one who figured out this relationship. And so the unit of heat is named for him. The unit for heat is the joule. You might think back and remember that the unit for work is joules, the unit for energy is joules, and now the unit for heat is joules. And so that's why I said you have to remember the idea that work, heat, and energy are all interchangeable and related. So they're talking about here, in the metric system or the SI system, the unit for heat is joules. They talk about the relationship between, this food calories that we sometimes focus on. Calorie is another unit for heat, and that's related to a food calorie. So 1 calorie is equivalent to a food calorie, kilocalorie, right? And so 1 kilocalorie is 1,000 calories. We don't get too much into the food calories in here. Like if you take a biology class where, they talk about food calories in terms of body functioning and processes, right? Brain function, kidney function, those types of things, how much energy is associated with those processes. In fact, when I talked about energy a couple of weeks back, there was information on various body functions and organs and the amount of calories that they utilize in their functioning. But we don't get too much in the food calories here. We're interested in joules because that has some connection between mechanical processes or motion and heat exchange. So let's take a look at how we determine the amount of heat that's being transferred. So we know that heat transfer is directly related to work and energy, but we need to be able to figure out how much heat is going to be exchanged. And there are 2 ways to look at this idea of heat transfer or heat exchange. One of them deals with heat transfer based on a temperature change. So if you have 2 substances that are different temperatures and you put them in contact, you're going to have heat transfer from the hotter substance to the cooler substance. Okay. And the amount of heat that gets transferred is based on a few properties. Number 1, how much of a temperature difference are we talking about? Number 2, how much of the substance are we talking about? And number 3 is what we call the heat capacity. Some books will say specific heat. Some books will say heat capacity. In any event, you'll see it written as C, the lowercase c. And so if you want to figure out the amount of heat that's being transferred, you can use this formula. If there is a temperature difference, okay? So the mass in this formula has to be in kilograms. And so when you use this formula, pay attention, okay? Q is the symbol that we use to represent heat, okay? This C is the specific heat and it's material dependent. The specific heat values depend on each substance. Each substance has its own specific heat value, C. So you have to look that up in a table of some sort. So when you solve problems that deal with heat transfer based on temperature difference, you use the formula that you see in the box. And I have to give you a chart or information on the value for C, because it depends on what material you're using. The mass, M, is in kilograms, and the temperature difference, delta T, means you look at the starting temperature and the final temperature and you take the difference. And this is where that knowledge of temperature difference on the Celsius scale and temperature difference on the Kelvin scale becomes relevant, because remember, delta T is the same no matter if you use the Celsius scale or the Kelvin scale, because you're just looking at the magnitude of the difference between the starting temperature and the final temperature. Okay. So they give you a table. Notice they give you a table here. Different substances, different values for specific heat. And notice they give it to you joules per kilogram degrees Celsius. The column on the right is in kilocalories. We're not going to worry about that, those values. We focus on joules per kilogram degrees Celsius. But remember, just as valid is joules per kilogram Kelvin, because they're talking about a temperature difference there. Okay. All right. They didn't list water on this table. If you look at the value for water, it's 4,184 joules per kilogram degree C. Water has the highest specific heat value of any of the substances listed here on this table. What is the significance of some materials having small values and some materials having high values? The smaller the value, the easier the material is to heat up or cool down. The larger the value of the specific heat, the more heat intensive the material is, meaning that it takes a lot more energy to heat it up. And once it's heated up, it holds the heat quite well. So for example, you see on there gold. Gold has a value of 129 joules per kilogram degrees Celsius. So it means that gold heats up very easily, but once you remove the heat, it cools down very easily. Water, on the other hand, well, you see they give the human body, but think about it. The human body is mostly water, right? So the human body, the water in the human body takes a lot of energy to heat up. And once the water is hot, it holds the heat very well. So that's the significance of having a smaller or larger value, but each material has its own value. The smaller the value, the better it heats up and cools down. The larger the value, the more difficult it is to heat it up and cool it down. The other heat transfer process that we care about is called the latent heat, and that deals with phase changes. So the formula that we just looked at depends on the temperature difference. The latent heat formula, which relates to phase changes, notice the formula in the box, does not depend on a temperature difference. But why not? Well, you might not have given this any thought, but this is how things work. As a material or substance is changing from one phase to another, the temperature stays fixed, meaning no temperature change occurs. Well, if no temperature change occurs, then delta T is 0. If delta T is 0, put 0 in this formula for delta T, and you get Q equals 0. That makes absolutely no physical sense, because you know that if you are going to boil water, you have to heat it up. So the fact that the temperature difference is 0 means you cannot rely on the specific heat formula. You need a new formula, and we call that formula the latent heat formula, okay? And so the latent heat formula, again, Q represents heat, M represents the mass in kilograms, and L is called the latent heat coefficient. That is material dependent, just like C is material dependent in the other formula for Q. L is material dependent in the latent heat formula for Q. And you have to be very careful because L can take two values. The latent heat coefficient has two values, LF and LV. LF deals with latent heat where you have freezing point transitions happening, and LV depends on phase transitions where we're dealing with the boiling point. And so you can see what's happening in this diagram. This is a diagram that looks at transitions for water. And so remember, whenever we are changing the temperature of the water, remember, don't think of water as just liquid water. Water is actually ice, liquid water, or steam, okay? Remember that. So anytime water is undergoing a temperature difference, we need to use the first formula, Q equals MC delta T. Anytime water is undergoing a phase transition, we need to use the latent heat formula. So let's take a look. In this particular example, they're taking water from minus 20 degrees Celsius all the way up to 120 degrees Celsius. But you have to do it in steps because you cannot change the temperature and the phase simultaneously. You either change the temperature or the phase, but not both at the same time. So notice we start off with ice at negative 20 degrees Celsius, and then we, quote, heat it up until its temperature becomes 0 degrees Celsius. So while you're going from minus 20 degrees Celsius all the way up to 0 degrees Celsius, you're changing the temperature, but it's remaining in the phase of ice. Okay? So while you're changing the temperature, you cannot change the phase. So while you're going from negative 20 degrees Celsius all the way up to 0 degrees Celsius, you are changing the temperature, but not the phase. So that means you have to go to the first formula, Q equals MC delta T, because there's a temperature difference happening. What happens when you get at 0 degrees Celsius? Well, remember, 0 degrees Celsius is the freezing point for water. So you would have to pause the temperature and keep it, it'll stay fixed at 0 degrees Celsius while all of that ice turns to liquid. Okay. Once all of the ice has transitioned to liquid water, then you can resume changing the temperature from 0 all the way up to 100 degrees Celsius. You can see on the graph, all the way up from 0 degrees Celsius to 100 degrees Celsius. What you're doing is you're changing the temperature, but not the phase. You're changing the temperature, but everything is staying in the liquid for water phase. So then you have to go back to when you're changing the temperature, Q equals MC delta T. Notice, while you're going from ice to liquid water, the temperature is staying fixed. So that's where you're using your Q equals ml. Once you change all of the ice to liquid water, the temperature can then begin to rise from 0 degrees Celsius to 100 degrees Celsius. So as long as the temperature is changing, you have to go back to the first formula, Q equals MC delta T. Once you get to 100 degrees Celsius, then the temperature pauses. Why? Because that is the boiling point. And until all of the liquid water changes into steam, the temperature is going to stay fixed at 100 degrees Celsius. So while all of the liquid water is converting to steam, you need to use the formula Q equals ml. Why? Because there's no temperature difference happening there. Okay. And then finally, once all of the liquid water has been converted to steam, then you can begin to raise the temperature of that steam from 100 degrees Celsius up to 120 degrees Celsius in this example, right? So in that last leg where you're going from 100 degrees Celsius steam to 120 degrees Celsius steam, you are not changing the phase because everything is steam, but you are changing the temperature from 100 degrees Celsius to 120 degrees Celsius. So this graph highlights a very important concept. You either change the temperature or you change the phase. You cannot do both simultaneously. Anytime you're changing the temperature, you have to use the specific heat formula. Anytime you're changing the phase, you must use the latent heat formula. Okay. How do you transfer heat? So we've talked about ways to determine the amount of heat that gets transferred, either with the specific heat formula or the latent heat formula. But how is the heat going to actually get transferred? Well, there are three methods: conduction, convection, radiation. Okay. So the first method of heat transfer that we'll look at is conduction. And I'm not going to go into anything beyond a basic definition here. And that is the transfer of heat between objects that are in contact with one another. So for conduction to happen, for heat to be transferred by way of conduction, the objects have to be in contact. Now, we're not going to get into rates of heat transfer. That's a little bit beyond our scope here. But they do show you thermal conductivity, which tells you what things are the best conductors. Okay. And notice those materials that have very low values are, poor conductors, and those materials that have high thermal conductivity values are good conductors. Okay. We're not going to go microscopic level because we're not, you'll focus on that in a chemistry class. We try to stay away from the microscopic level and just think about conductivity as this larger process, heat moving from hot to cold when objects are in contact. Another method of heat transfer is convection. And they talk about, some various modes of thermal convection here, but I'm just going to give you a simple definition. And that's what I would expect you to be thinking, the level I expect you to be thinking on. So convection is heat transfer by way of fluid flow. Convection involves heat transfer by way of fluid flow. Okay. And remember, fluid could be a liquid or a gaseous fluid. We think of water as being a liquid fluid, but air is a gaseous fluid. So heat transfer by way of fluid flow. And they talk about, give you an example of convection here. You can take a look at that, but it's not anything I would expect that you would, have to discuss with me on any level. All right. Thermal radiation, that is the last method of heat transfer. And that is heat transfer by way of light. Light. A lot of times you will see it referred to as electromagnetic radiation. But if you just keep in your mind that when we say light, we're not just talking about visible light. We're talking about all types of light on the electromagnetic spectrum. Heat transfer by way of light. That can be microwaves, that can be infrared, that can be UV, that can be visible light, that can be radio waves. It can be all sorts of electromagnetic radiation. So heat transfer by way of light. So the three methods of heat transfer: conduction, convection, radiation. We're not going to get into rates here either. We stay away from that. And as well as emissivity and black body radiation, where that's a little bit above where we want to go in this course. So the final thing that I'll talk to you about is the first law of thermodynamics. And notice what I clicked on here. I do have a supplemental thermodynamics notes here. Let me see if I can get it to open this time. Yeah, there we go. We'll take a look at that briefly, and then I'll show you one of the other nice websites that I've made available to you. So I'll try to get through this fairly, with enough detail, but fairly quickly, as I mentioned, so that we can kind of wrap things up today. So this thermodynamics looks at the heat transfer and its relationship to work. Thermodynamics. I like to say, to be absolutely clear, the relationship between work, heat, and energy, because they're all interchangeable, okay? And so you see, it tells you here what work led to the formulation of the first and second laws of thermodynamics, and then later the third law was added. And then after all of that, they went back and came up with the zeroth law. So there are 4 laws of thermodynamics, okay? And I've introduced you to the zeroth law because it's the most basic. We're not going to focus on the second and third laws here. What I want to take a look at is the first law. And to do that, I think I can explain it here, and then we'll take a look at a visual on the NASA website that I bookmarked for you, okay? So the first law of thermodynamics looks at the relationship between energy, which they call delta U, internal energy, delta U, heat, Q, which is a symbol that we're used to seeing because we saw Q in the other formulas, and work, W. So you can see that the first law of thermodynamics deals with work, W, heat, Q, and internal energy, delta U. In particular, they're looking at the change in internal energy here. So if we want to know how the internal energy of a system changed, look at the amount of heat you put in and the work you got out. The difference between the heat that's put in and the work that's done by the system, think about the heat put into a system, the work done by the system, or the work out of the system. The difference between those two is the change in internal energy. And that is the first law of thermodynamics, okay? But let's take a look at another visual that I think will clarify this more, All right, so I'm gonna go to this NASA website. Can y'all see that? I think the sharing is still pretty good there. Am I right? Somebody? Can y'all see that on the screen?
Yes, we can.
Thank you very much. Okay, so I'm gonna go, we looked at the 0th law. Let's go look at the first law. Notice I like this website because I can just click right into it and it opens it right up. And there's a nice visual, okay? So you could imagine that you have this system. In this particular system, they're modeling a heat engine of some sort. I'm not the greatest mechanic, but I have a general sense of how, you know, old school engines work. So the fuel that you put into your vehicle is transferred into the engine. That engine has a piston. The piston is the red item. And as the piston moves, it moves down, it compresses the fuel. The yellow and black dots, that area represents the fuel. As the piston moves down, it compresses the fuel, which causes it to ignite. And then that, you know, you get heat being added to the system as that fuel combusts. That's why they call it what, an internal combustion engine, right? So as that fuel heats up, that piston can do work. As that piston moves as a result of that heat done, it does work, which ultimately gets transferred to some type of drive shaft that moves the, turns and moves the wheels, right? So you get a connection between this heat energy that's being transferred and the work that the engine is actually able to do. So in this particular diagram, I like because it's very clear what they're calling energy, E, right? And if you imagine taking snapshots of the engine at different times. So at the beginning, you have energy 1. At another time, you take a snapshot, the engine has energy 2. If you take the difference between energy in position 2 minus the energy when it's in position 1, that is equal to the heat put in and the work, the difference between the heat put in and the work done. Okay. And that is called the first law of thermodynamics. The difference between the energy when you look at different states in the system is equal to the difference between the heat transferred into the system and the work done by the system. Heat in, work out. And in particular, the first law of thermodynamics says that Q minus W is not going to ever be equal to 0. You can think of it this way. You are never going to have a perfect engine because you are never going to get 100% efficiency because you are never going to have 1-for-1 Q in is transferred to W out. You put heat in, think of it. Put gas in, the car goes. That's the work. Gas in, that's Q. W out, that's the movement of the car. You're never going to have 100% fuel efficiency, meaning all of the fuel that you put in Q is never going to equal to the motion of the car, W. Some of it's always going to get wasted. How do you know it's going to get wasted? Just touch the hood of your car after you've moved it around and you'll notice that it feels warm. Well, that's energy being lost, right? So this first law of thermodynamics talks about the relationship between work W, heat Q, and energy E. And so the change in internal energy is equal to the difference between the heat in and the work out. Okay. So again, all of those resources that I just covered are available in the readings and required viewings. I would take a moment, go back, look through your textbook material, check out some of the videos that I bookmarked for you in Khan Academy. And then, of course, go back and review the notes that I provided for you. In addition to that, when I post the announcement for the video today, I will include a link to some extra notes resources that if you take a look at them, you will see that there are some sample problems worked out dealing with heat transfer, specific heat and latent heat. Those are very helpful, okay? All right, so at this point, I'll stop the share and ask if there are any questions about anything I've covered. Okay, so here's what you have to agree to do for me. If you're working this week to complete the assignments for the week, you need to reach out to me if you have questions, okay? So you'll be completing a problem set that deals with last week's material. You'll do a discussion that relates to this week's material. While you're working on those items, if you have questions, reach out to me, okay? Next week, we're gonna talk about waves, and I'm also gonna talk about the project again. Waves is a fairly short topic area that I can cover in a short amount of time. And then we'll spend some time talking about the project next week. All right, so that's where we're going. Any questions? All right, if you don't have any questions for me, we're done for today. I appreciate you joining our short session today. Have a good evening.